The physical universe operates with infinite fluid precision, but to calculate physics on a computer, you force that reality into a rigid mechanical box. At the hardware level, a standard processor register is a literal finite container. It has exactly 32 slots for ones and zeros. Packing all 32 of those physical slots with ones yields a maximum value of just over 4 billion. 4 billion sounds large, but it is far too small to calculate cosmic distances. This integer format fails completely the moment you need to represent a fraction or a decimal. In the early 1980s, this strict physical limitation caused a crisis. Every major hardware manufacturer invented their own custom proprietary method for processing decimals to try and bridge the gap. This fragmentation meant a physics equation calculated on an IBM machine would yield completely different math, or simply crash when ported to another brand. The IEEE 754 standard was a universal treaty. It solved this mathematical chaos by teaching every machine to make the exact same compromises. IEEE 754 divides the 32 bits into 3 blocks. The first is a single bit dictating if the number is positive or negative. Next, the 8-bit biased exponent dictates the massive scale or microscopic size of the number. A specific value added to this exponent creates a bias, ensuring the processor only computes positive binary values. Finally, the remaining 23 bits, the Mantissa, hold all the high-resolution precision trailing the decimal. By decoupling the scale of a number from its fine detail, this architecture allows a tiny 32-bit physical space to process both the width of a galaxy and the width of an atom. What happens when a calculation hits a boundary or breaks the laws of math entirely? This diagram shows the rule for numbers that grow too large. An exponent block filled with all ones, paired with a fraction block of zeros, is the universal code for infinity. For mathematically impossible scenarios, like dividing 0 by 0, the standard introduces nan, or not a number. This error state triggers when the exponent hits all ones, but the fraction contains data. The standard also protects the small end of the scale with a feature called Gradual Underflow. Specific bit patterns prevent these microscopic calculations from suddenly dropping to absolute zero and ruining delicate physics simulations. These edge cases act as a foundational architectural safety net. They ensure that when reality defies arithmetic, the physical microprocessor doesn't crash. Let's bring this down from theoretical architecture to a highly practical calculation. Take an unassuming, simple decimal, 0.085. This visualizes computing's central paradox. Attempting to convert 0.085 into binary fractions generates an infinite, repeating sequence of bits. But remember the hardware limit. The architecture allocates exactly 23 bits for the fraction. It cannot store infinity. The computer executes a compromise. It severs the infinite sequence and rounds the last available bit up or down. As a direct result, the value stored in memory is no longer exactly 0.085. It is an incredibly close approximation. These microscopic floating point rounding errors happen thousands of times a second in almost every piece of modern software, from global financial spreadsheets to the physics engines powering video games. When we see precise decimal numbers on a screen, we are looking at an illusion. IEEE 754 works because it acknowledges a fundamental truth. To capture an infinite universe inside a finite machine, you must sacrifice absolute perfection.